Wow, what tepid applause. Thank you.
Hey, my name is Chris Craik. I work on Android UI Toolkit.
And I'm Chet Haas. I also work on the Android UI Toolkit team. And today, why don't we talk about performance? It's been a while since we've had a performance talk, so we thought we should do it again because we like talking about performance. For this year's performance talk, we wanted to make it a bit more use case driven, tell you a little bit about how rendering works, some of the changes that we made, some of the improvements around performance, but also go through some steps of how you would actually find out what jank is and how to fix it in your applications. So let's do that. UI performance. Hey, there you go. So we talk about frames per second, FPS. It's a really good metric. It's a good way for understanding what's going on in your application, but it's actually better to think about the duration, right? So it's not how many frames per second you can hit. Honestly, the display is hitting 60 frames a second all the time. And then you need to sort of hit the same number of frames for your application in each second. But it's really better to think about the duration that each frame is taking. How long is that frame taking to actually draw? Because you're not going to fit within that window if you're taking too long to fit, right? So if you want to fix the jank in your application, if you want to fix the stutters, if when you're flinging and scrolling that list, there's skipped frames in the middle and the user is seeing this janky behavior, fixing that means fixing the frames that are simply taking too long. So also it's good to think about consistency. It's great if you can have 60 frames per second most of the time, but then occasionally if you're dropping several frames in a row, that's not good. What you really want is consistent behavior. So chasing jank is all about finding the places where you're dropping those and making sure that you're fixing the bottlenecks that are contributing to those. So let's talk about time. Let's take a look at time going forward from the left to the right. Sorry, from the left to the right. And take a look at what's happening in the UI space. So if you think about these vertical refresh syncs, on every 16 2/3 milliseconds, typically on a typical display, we're getting a vsync request, right? So this is the hardware sort of posting the frame to the screen. That is when the user sees something. So divide that by 60, second divided by 60, 16.2/3. I can go over the math later if you need me to. Then if you map frames onto that, each of these frames, this is sort of these gray boxes are what your application is doing in order to post that information to the screen, right? So ideally, your frame would all of the stuff that needs to happen for that frame would be within that 16 2/3 milliseconds. I need to stop saying that. I'm going to say 16 milliseconds, and you can interpret it however you want. So the beautiful icon that I hand drew myself down at the bottom of the screen, that's the user seeing things, right? So on each of those vertical syncs, they are seeing whatever the hardware buffer is posting to the screen. So they're going to see it, there. But if there's a problem when you're rendering, if one of your frames takes too long, then the user is not going to see that. They're going to see exactly what they saw in the previous frame because you took too long in your application and you skipped a frame. So that's jank. That's the stutter that we need to try to analyze and fix. So let's take a little step back and say, OK, how does rendering actually happen in the UI toolkit? Well, there's the app perspective, so what's going on in your application, and then we'll take a look at what the framework is actually doing on your behalf. So here's some simple code. I keep looking back at, OK, so you can see on the screen back here. Here's some simple code. We have this color. Things are light gray right now, and when the user clicks in the middle of this custom view, we're going to change the color. We're going to tell the view that it needs to invalidate itself, and then it's going to redraw in the new color. So user clicks on the screen. That signals, that sends an event into the onClick method. We're going to change things around. Then we're going to invalidate. And that invalidate is going to cause a later call to onDraw. It's not a serial thing. It doesn't directly call onDraw, but it tells the system, hey, things need to be redrawn. And then a later call will filter into the onDraw method. And then the onDraw will draw into the canvas. And that will eventually be posted to the screen through all the operations that the UI toolkit is doing on your behalf. So from the platform perspective, what's going on is several things in a row. First of all, on any given frame, when we get that vsync request, we process inputs. So if the user is clicked, if the user is scrolling or flinging, that's where we get that information and do something based on it. If there's animation, if they have let go of that scrolling list and it's now flinging and just posting events so that it gets updated as the list moves in space or as views move around on the screen, we process those animation events. We change the properties. That causes invalidation so that things can get redrawn appropriately. Then, if necessary, we do layout. So if something changed in your application that changes things' size or location, that's when we measure and lay out the things that need to be changed, again, causing invalidation and redraws. And then we actually do what we call record draw. So this is what we were seeing on the previous slide in the onDraw method. This is where you turn whatever you want to do into drawing operations that we then receive and store internally. So you're going to say, well, Canvas, draw this new color. So you're recording the commands that should happen in order for us to then draw the right thing under the hood. And then finally, render, and that's our stage in this, right? So you do everything in the first 4 steps in your codes, or for standard views, we're doing it, and then we handle the rendering, and that's basically the transformation of those recorded draw calls into whatever we need to do at the bottom layer. I'll give you a hint. We turn it into OpenGL or GPU commands that we then send to the GPU. So if we look at that in beautiful, brilliant colors, which we're going to use in some upcoming diagrams, we have these 5 stages, right? So in any particular frame, the boring gray box there, it's actually broken down into those different stages. In our previous example, in that simple application code, we didn't have all of the stages because there was no layout required. All we were doing was changing a color. So we had the input of the onClick, and then we had the record draw of the canvas operation to draw in the new color, and then the rendering operation that resulted from that. In a typical, yeah, just like it says on the slide. In a typical application, more general frame, then you're going to have all of the steps in there. So we may process some input and some animation and some layout and record and then render. And all of these things are happening in a sequence, right? So this is the order of operations. In reality, we actually have 2 threads kicking in as of Lollipop, where we came out with a render thread technology, which we've talked about before, where we process all of the application space stuff going on. Those first 4 steps in the application space are on the UI thread. And then we have this separate thread that's actually handling the rendering. They still happen in series, in sequence, because the render thread doesn't know what to render until you tell it. But the render thread can also do other stuff asynchronously from the UI thread. So we can send over some of the atomic animations that it can process in the meantime. But in general, you do all this stuff on the UI thread, and then we sync that information to the render thread, and then the render thread on that separate thread will handle talking to the GPU. So in a well-behaved application, in a typical, let's say this is a scrolling or a flinging situation, and things are well-behaved in the application, and you draw relatively quickly. This is what things look like. Again, the beautiful eye icon at the bottom. The user sees the frames happen. Bam, 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 bam. Everything's happening within the 16 millisecond barrier. But in a typical janky situation, all of a sudden something took longer, right? So here we see that the input command took a lot longer. So maybe when the user clicked, some expensive operation was performed. Somebody made a web service call, or more typically, you created or you bound a view. You did some expensive operation that caused us to do a lot of work, pushed out the length of time that you're spending doing all of that recording of draw operations, and then the rendering operation necessarily slipped into the next frame, and the user missed seeing that input because it didn't hit the barrier. So that's the jank, again, that we want to fix.
All right, so let's move over to talking about what do. You have problems in the application. You see now, as Chet has described, what can happen when a frame takes too long. Let's talk about the process that we call dejanking, stepping through your application and finding and fixing these problems. So the first step in dejanking your application is to run a release-ish build. And so what I mean by that is make sure that you're running with debugging off. If you're running with debugging on, Art has to add in a bunch of different checks and verification steps that can add a little bit of time and skew your results a little bit. So we recommend overwriting that or testing an actual release build. So the second step is to inspect your app visually. As you're scrolling through lists, if you see any jank occurring, just visually detecting that. If you see an animation, definitely start with the most key important parts of your app. Lots of you guys have a primary scrolling list, great place to start. If you happen to be one of the kind of people that can't see jank, if you just see, oh, well, it looks fine to me, you can turn on profile GPU rendering. And that gives you all of these bars at the bottom, which will tell you when you pass that particular threshold and give you a little hint as to what might be happening based upon the color. And there's some documentation about that online, but the real next step after that, you've seen some jank, you see, oh yes, when these items come on screen, or the first time that I load this particular part of the UI, you figure out what the interaction is, and you say, okay, what do I do next? Well, the next step is generally systrace. Systrace is a tool that exists in the SDK in the platform tools directory. You can also get it off of GitHub if you want the absolute freshest version. And so from here, we're gonna do a very quick live look through what a systrace actually looks like. So this is what you might see when you pull up a systrace for the first time. So in this particular example, I was scrolling through a recycler view in my app, and I saw, oh, there's some janky frames. I can see some visual stuttering. And so I captured a systrace over the duration of that time. And now I pull up a systrace, and oh my goodness, there is a lot of information here. There is a lot of noise. It is really hard to see what should I be looking at. So first and foremost, what you can do is you can look here on the left. You can see, okay, well, there is kernel, there's potentially other processes. You know what I'm going to do? I'm going to ignore everybody else for now, and I'm going to scroll down until the top process, the only thing that I can see right now is my package, android.janktown. And in fact, you can even go further than that. You can look on the left here. This tells you, in fact, individual threads that we care about. And as Chet was talking about, there are two threads that matter here. There's the UI thread of my app and the render thread. So I'm going to scroll down further until all that I can see at the very top of the screen is mostly that. And so from a very high level, even just looking at this trace without knowing much about it, I can say, OK, the time in this trace goes from left to right. On the leftmost, we have 0 seconds going all the way further. And if you can't see the specific details, don't worry about it. We'll go into some zoomed-in screenshots later. But even from this very high-level view, I can say, oh, well, I've got a lot of tiny little slivers here, these little pulses. These are frames. OK, great. Most of that looks incredibly consistent, looks really smooth, and it looks to be repeating regularly. However, there are some big visual standouts here. And this is very often what dejanking is looking for these particular standout frames and investigating. So if I zoom in here, I can start looking at exactly what's going wrong in these frames, and I can start clicking around, figuring out exactly what the problem is. And just so that you can see that, we're going to switch back to slides and show you the screenshots in particular. So this is one of the simple frames, zoomed in pretty significantly, that we saw earlier as those very frequent and very regular pulses. Now, these were very nice. They looked like tiny little slivers before, but let's go ahead and look at them to see what a baseline is. So first of all, one of the tricky things about systrace is there's a lot of data here. There's a lot of things to click on, but one of the nice features is that most of these UI thread components, click on it, systrace will do its best to try and explain it to you. So if you click on this particular top of the UI thread, which means this is the topmost traced section, this is the biggest chunk that represents the UI thread work. If you click on that, at the bottom of the systrace UI, it'll say, oh, OK, well, this is what Choreographer is. And in fact, here it'll even link you to the documentation where it describes on d.android.com how Choreographer works. Similarly, if I want to look down at draw frame, that's the render thread component of the frame. And if I click on it, I get a similar explanation. There's lots of this for all sorts of tracing throughout systrace, especially on the UI and render thread where you might be most interested. OK, so now that we know we can click on things, we can get a little bit more information that way. Let's go through exactly what does this frame look like? What's it doing? So the very first thing we see here is an animation callback. If you click on this, it'll say animation, or if you zoom in, you can see that. And I'm just going to go through these that way. So this is animation exactly as Chet was talking about it before. And if we saw before, we had a whole lot of frames. And I told you it was a recycler view. So there's one very common reason for a recycler view to be animating, and that's flinging. Just the fling animation itself executes recycler view's actual translate and inflate work as part of an animation callback. And then the other stage that Chet talked about before is record draw. Well, this makes sense as well because recycler view is invalidating, sliding things around, and drawing. OK, we kind of get some context for what it's doing. And in fact, if you click on this part of of the animation, which is inside animation, this is recycler view scroll. So recycler view scroll is actually going really, really fast here, and that's because recycler view is doing very minimal work. In fact, if we look at the amount of time taken by this UI thread frame, it's 1.25 milliseconds. That's great. The whole frame finishes in less than 6. This is a great frame. Congratulations. Now we look at a little bit slower of a frame. Now this one's actually not terrible, but let's look at how it differs from the previous one. So first of all, we notice that there's a measure pass in here. So something in the hierarchy requested layout and got remeasured. OK, good to know. And then another thing down here, we see upload bitmap. So the first time that the render thread sees a bitmap and needs to display it, it will be uploaded to the GPU, uploaded to OpenGL so that the GPU can draw it really fast. Now that first upload is a little expensive, and we'll talk about that a little bit more later. But really, if we look at it, well, the UI thread takes 4 milliseconds. The entire frame finishes in less than 13. This is not a problem frame. This is fine. But now let's look at the really bad ones. These were the ones that we saw from very far away. OK, something is definitely going on here. But if you're new, like, what's going on? How do I figure out what's going on? So actually, if you click on this part that says RV create view, it'll describe to you that this is basically your adapter's callback for onCreate view holder. This means that recycler view needs a new view, and it's creating it. And in fact, if you look directly below that, well, a lot of the time that takes up this create view portion is that it's inflating. And inflating, especially with the complex items in my recycler view, can take a while. Well, that's unfortunate. The next part here, onBind view holder, that takes about 1.5 milliseconds. Not great, but OK, well, what can I do? Yeah, this UI thread frame took about 20 milliseconds on the UI thread and total to be about 27.4. Not great. We are definitely going to jank that frame. So this is actually, this process is one that you might go through yourself. But in this particular case, we realized, well, this is something that we can help you out with in SupportLib. And this is a feature that we worked in for exactly that purpose. So let's go back and talk a little bit about what recycler view does. So recycler view is the primary SupportLib component for displaying a dynamic list of content that needs to show views dynamically, that needs to scroll infinitely, potentially, or display more content than what is attached to the view hierarchy. So what do I mean? Well, I mean, if you have these 4 items partially visible in your recycler view, you start scrolling, and all that recycler view needs to do is handle these 4 particular items. In fact, all that it has to do is offset them very slightly, and that's the amount of work that we see. And in fact, if you remember, the very first RV scroll that we highlighted, it was tiny. It was trivial because recycler view did very little. But once we get to the edge of this particular list, well, what happens? Now we suddenly might see some jank, because this is a frame in which something interesting happens. For the first time, this list has 5 items in it. That means it can't get an item to be recycled from previously. That means this message icon had to be inflated. Well, so that's the old way of recycler view working. So let's go back to a sort of simplified version of what we saw in the systrace. Let's say again that this happened during Fling. We have 2 frames that look totally fine. They have short UI thread durations and very reasonable render thread durations finished before the deadline. But then suddenly you hit a big chunk of animation. And as we know, in this particular case, that's because recycler view is doing its create and bind work. So we see something funny here, though. With render thread working as it does, the UI thread is totally idle for the 10 or so milliseconds in advance of this new frame coming on. Well, it's not hard to predict that the Fling is going to continue. I mean, that's kind of what animations do. And this create work, it actually could have fit right there. So this is exactly what we do in recycler view prefetch. We started looking ahead to new items that are about to come on screen and basically stealing work from them, realizing, oh no, that's going to do a lot of work. Let me steal a little bit of that. Let me go ahead and do that inflation early so that we don't have to do that on demand. And this is what it looks like in practice. So this is a systrace from the exact same app. All that I did was update the SupportLib to get this feature. And suddenly we get an RV prefetch event in systrace. Again, click on it. It explains the prefetch feature, what it does. And we see, wow, that's 13.5 milliseconds that we pulled out of the next frame. We saved a huge amount of time by work stealing. And now, this is one great example of something that the support lib has done, but it's absolutely the process that you can go through for looking for problems in your own app. Support lib can't solve every problem this way. But let's talk about prefetch a little bit more. So there are some caveats. So what happens if the item isn't actually needed? What happens if we prefetch an item and suddenly, just before that item is about to come on screen, the user decides to tap the screen, stop the fling? If the fling is stopped, if you don't end up needing the item, or if something else comes in, some last-minute arrival of new data, you might have done the work incorrectly. And really, that's fine. 99.9% of the time, prefetch is going to make the right decision, and you might waste a little bit of work in that particular case. What if there's no render thread, though? If there's no render thread, we just don't try and prefetch to begin with right now. So because render thread is on the vast majority of devices, you get this on most devices for free by just using a recent version of the support lib. But on older devices, this feature doesn't work. So availability, this was actually introduced a while ago with support lib v25, but it's been getting better, and including with the most recent beta of 26. This feature is built into default layout managers, so if you just use a recycler view, horizontal, vertical, whatever, with linear or staggered or grid layout, you just get this for free. This is just from updating to the newer support layout. However, if you have a custom layout manager, if you wanted to do something completely custom, or if you wanted to subclass one of them in an interesting way, just be aware that you may need to override this particular method, collect adjacent prefetch positions. And this is how you, in your custom layout manager, can get the exact same behavior, and you can look at the implementations of the other ones. And you can read more about this in Chet's wonderful post about recycler view prefetch on Medium. But let's step back a little bit and talk about, well, what happens to Jank? Well, we saw in this particular case that recycler view having bursty workloads could cause Jank. But let's talk about sort of stepping back, what has historically been the problems for Android and Jank? So one of the oldest ones that we've thought about is garbage collection. Garbage collection historically had been a significant problem on Android, but this has been something that the platform has been improving steadily. So GC for alloc was essentially fixed in L with art. I've looked at hundreds of traces. I haven't seen a blocking GC on any but the most egregiously allocating apps. GC is not a huge problem, but even still, the runtime keeps improving. Runtime keeps getting better at GC, lowering the overhead of allocation. OS thread scheduling. So this is a particularly interesting one, where on older versions of the kernel and on older versions of Android, sometimes the platform would just make a bad decision about when to schedule your application. This has been improving greatly, especially in and O, but it is unfortunately kernel specific. So that means that it's not guaranteed to be in every in or O device. But definitely look for newer devices if you're looking specifically into thread scheduling, if you're trying to make sure that your work is running exactly when you want it to. Rendering is an interesting one. I work a whole lot on rendering. Rendering, specifically, one of the things that I remember Chet and Roman talking about years ago has been view alpha. If you, let's see, there's has overlapping rendering, there's set layer type hardware, there's some other callback somewhere that I need to remember. Well, we try to improve that. So we started adding auto hardware layer in M. Get that for free. In M+, you can still use hardware layer to avoid that problem. But we've gotten even further improvements in N, improving the worst case. Bitmap uploads are another one that I talked about earlier that had that can cause a significant amount of delay in first displaying your bitmap. But we added a new feature in N, prepare to draw, on bitmaps that would allow bitmap loading libraries to asynchronously start that work early, and that's starting to be adopted by them. View recycling, just as I said before, was another common cause that basically support lib has significantly improved for you. So added in 25, more improvements to come there. And you can go back and watch the recording of the art session from this I/O if you want to learn more about what art has been doing. But I wanted to go through all of those because I think that tells you a lot about how the platform has been improving and trying to get to the point where the only sources of jank in your application are ones that you can solve. So let's talk a little bit about some of the sources of jank that might happen in an application, that might happen because of something that's going wrong inside your app. And there are a lot of them, but let's just go really quickly. So issues in recycler view, we talked about issues with recycler view needing to inflate, doing that work at the last minute, lazily, possibly causing 10 milliseconds or more of work in a single frame. But there's a lot of other subtle issues in recycler view that can cause unnecessary inflation, and talk a little bit more about that. So bitmap painting on the UI thread, one of the most common reasons for your draw callback to be very long is because you're trying to cache some work, cache some content in a bitmap. But unfortunately, drawing to a software bitmap can take a lot of time, especially if it's anywhere near screen size. Canvas calls, there are a few canvas calls, namely draw path if you're mutating your path frequently, save layer that can be somewhat expensive. And we've actually gone out of our way to document some of these, and I'll mention this coming up. But let's go quickly to an example of Binder, because this has been one of the favorite investigations of the Android performance team in the past release, has been looking and fixing Binder problems. So Binder is the IPC mechanism on Android. If you want to talk to Window Manager, or if the view hierarchy thinks you want to talk to Window Manager, you're probably going through Binder. If you're talking to another person's content provider, if you're talking to Surface Flinger, if you're talking across IPC, you're probably going through Binder, and Binder has tracing. Now, unfortunately, IPC is often very expensive, and truth be told, it can be really easy to accidentally add to your application. Here's a particular screenshot of a systrace that has a lot of Binder transactions going on during recycler view scroll. If you look at it, the Binder, oh my goodness, and then they're just running another callback on the UI thread, running lots of Binder. All of these are pretty significant. It's a 21 millisecond frame. It's not doing any inflation. It's not doing anything that should absolutely take that long. It's just Binder overheads doing work that they really shouldn't be doing on the UI thread. So tracing Binder can help a whole lot, and that's on by default in the newest versions of systrace. But to summarize, there's a lot of reasons, and we've documented a whole lot of them. If you go to d.android.com/vitals, we have a lot of the material in this presentation, a lot of those samples that I went to in more depth with code examples, so on and so forth, on this website. And so now I'm going to pass it back to Chet, who's going to talk about maintaining performance in your app.
I should point out, too, that the document site that Chris pointed to is new. It was just posted, what,
yeah, just
yesterday?
Wednesday, yeah.
So if you think you know the performance docs on the site, you might want to check it out anyway. Much more detailed, in-depth info, and the documentation team was working really closely with the engineers like Chris and other teams to get the information that was really accurate and deep to help you with this dejanking. So let's talk about how you can find and fix and actually maintain your own app performance. It boils down to sort of 4 steps you can think of. One is that you can gather user statistics, so actually figure out where the problems are. You can add your own tracing. It's important to note when we're looking at all the systrace stuff that Chris was showing, that's not a sampling profiler. It's not a, we're not seeing like per method calls. That's not all the stuff that's going on in your application. Those are specific traces that we have instrumented the framework and the platform code with. So the only thing you're going to see in systrace are the traces that we've actually added to the platform, right? Because if we add a ton of traces, then it's going to slow down the application. So we add it in the places where it really makes sense. So you can actually add your own tracing stuff. We'll show you how to do that. You can add jank tests. So maybe you actually need continuous tests so that you can tell when you implement a change and you have a new build of your application and your performance goes down. Wouldn't that be nice if you knew that instead of depending on lower ratings on Play Store because your users are the first ones to see that? Maybe you could actually have continuous tests that can catch that for you. And then finally, use the tools. He went in depth on systrace, but it's worth thinking about some other ones that should be a part of your normal toolbox when you're developing. So one of the things I should point out in looking at the user stats is this is a screenshot of a dashboard that is now, it's sort of a theoretical screenshot. This is, we don't actually give gray boxes. That would mean nothing. So this is from a talk that the Play team gave on Wednesday and talked about the different metrics that they can provide on the dashboard now. So there are metrics that are being calculated and stored on the device that, depending on whether the user opts into it, may be uploaded, and then it can be information on your dashboard for your application. So you can see what people are actually seeing in the real world, including jank stats. So how many of your frames are coming in, that's sort of a histogram of these duration buckets. So how many frames are coming in at each level of that histogram. So you can get an idea not just for how your application is doing in general, but also if you just updated it and things got worse, wouldn't that be nice to know? That information that's being aggregated and shown in the Play dashboard is actually coming from internals that we have in the platform that were injected in the N release, where we have this thing called frame metrics, and we have an API around that as well. And we compile this thing at a very low level, but you can listen in on that. You can implement this on-frame metrics available listener and get the per frame callback data that says, okay, here's what the duration was for each of these individual things. And if you think about, if you've done the GPU profile or the on-screen profiler, we saw the screenshot earlier, all of that information is exactly the durations that you get from the frame metrics listener. How long did input take? How long did animation take? How long was the total duration of the frame? So you can get all of that information, aggregate it yourself, and then upload and analyze to your heart's content. We simplified that a little bit in v26 of the support lib, so the beta release should have those bits now. So instead of listening per frame and getting the durations and then needing to aggregate them, we aggregate them for you, so you can get this sparse int array of duration buckets, basically a histogram. And then again, you can compile, aggregate this stuff on the device and then upload it to whatever server you choose to analyze offline. So the Play Store dashboard does that for you for your overall application. But if you want to instrument particular flows in your application that are really sensitive or important for you to get right, then you can choose to do that with the frame metric stuff. Custom tracing, so as I said, all of the traces that we saw in the systrace example that Chris was showing were the standard traces that we have on the platform, but you have the ability to add your own traces in your application. So you should think about doing this for some of the things that you think might be more expensive, where you know you're triggering, I don't know, layouts or whatever. You want to do it for when you're binding views or creating things that may be expensive. Maybe you want to add a trace there and sort of see what that time is going to be and what it looks like in systrace. It's important to know that the more you instrument, the more time you're going to spend actually outputting the instrumentation information. That's why we don't have per method instrumentation. On one hand, you don't want too much information in systrace because then the important information gets lost, but also you don't want to actually skew your times by the instrumentation calls that you're actually making. Right? So same thing is true for your application. So you should think about, if it's going to take greater than a half a millisecond, then the overhead of the instrumentation is going to be in the noise. But if it's much faster than that, you probably don't want to do that, at least not on any permanent basis. And performance tests, it's always good to have tests anyway. Wouldn't it be nice if you actually knew when you were triggering a performance problem? This is especially true for big apps and big teams. So if you have many developers chucking code into a common code base, it's good to have an automated way of detecting when problems come in. If you have developers chucking code in and they are not as familiar with your architecture or your practices, then you want to be able to detect that earlier instead of catching at the user level. And you want to, in particular, have tests around the areas of your UI that are more important, right? So if there's a common feed, some common list view, recycler view situation that people are going to be going into all the time, if that's where everybody lands, well, create some performance tests around that and make sure that that code stays tight. You can gather the data on the user sides, on the device side and app side and frame metrics aggregator, or you can also do it on the host side. So you can run these command line tools like dumpsys GFX info that will get all of that information. GFX info, again, this is the same. It's a different view into exactly the same kind of duration data that I was talking about earlier that you see in GPU profiling, that you see in frame metrics aggregation. And in particular, you want to watch what's going on with the different percentiles of your app. If you skip a frame occasionally, no big deal. If occasionally you have a 700 millisecond frame drop, that's probably a big deal. Or if you have 10% of your frames that are actually missing their boundaries, that's a big deal. right? So just pay attention to A, what your app is doing, and know what the performance is like, and try to get that performance as good as you can, but also pay attention to what's changing over time as you update that app. Make sure that you're not losing performance as you do it. And then finally, use the tools. So we talked about profile GPU rendering, something you can enable in developer options very easily, just sort of see where things are going, what's going on in the device when you fling your recycler view or whatever your common UI case is. That green line is important. If you're going above the green line, you miss the 16 millisecond boundary and you janked a frame. This one looks like a particularly janky frame. I don't think they're making any frame there. So at least they're consistent. They got that going for them. So you can do that on the device. This is more sort of at the debugger and developer level, just sort of see where things are at. Again, it's using the same information that we compile at the lowest level and just putting it on the screen for ease of use. Android Studio just came out with some new profiling tools in their latest release. They were talking about that in some of their talks this week, so you can check those out in the recordings on YouTube. In particular, for this audience, the CPU monitor will give you information about what's actually going on in all of these method calls. It gives you a good idea in general about where the performance is going on is going in your app, and also the GPU monitor, which is again another view into like how fast you're rendering this stuff and whether you're hitting the 16 millisecond bound.
Yeah, in fact, I want to say, if you're ever familiar with the previous tools that used to be part of the SDK, the trace view that was built into Monitor, this does the same thing, but with a far better UI, far more usable, and actually far more correct data as well. So far more advisable.
So the way I view the different tools, so we saw the deep dive in Systrace, and especially when you first see Systrace, you're like, I never want to see that tool again. There's just so much information there, and you're not quite sure what to do with the information. That is the tool that has all of the information. It just takes a little bit of getting used to in using it to see how it works and how you can divine the information you need and add the custom traces that you want. I think an easier way to get into it is you can dip in slowly by using the much easier to use, higher level view of what's going on with the Android Studio tools. And then if there's a particular source of jank that you're trying to chase, know that Systrace is a fine-grained tool that's going to help you chase that at a much deeper level system-wide. And finally, not on topic, but for this crowd that's interested in performance, you may want to try out a developer option that will enable this alternative render that's not on by default. But you can see how your application behaves with this for possible future possibilities. So it's the Skia renderer. You can go into developer options and enable that and just make sure that there's not an issue there. If there is, it'd be lovely to hear about it. That's why we're mentioning it today. There are some resources that we mentioned. I will bring them up again. Again, check out the Vitals page on d.android.com. In particular, they have a jank section called Slow Rendering.
Yes.
And there are some important I/O sessions to check out on YouTube. They're probably posted already. Tim Murray gave a great overview about Systrace and system performance in general. So Android performance overview. The Art Talk talked about performance and memory improvements. They did some pretty amazing stuff on both the runtime side, runtime improvements, as well as the GC side. So now they have concurrent garbage collection. There's almost no pauses anymore until they need to take a full GC eventually. And they can compact in the foreground. You get a minimal sized heap. You get much faster allocations as well as collections. So the details for all of that stuff are in the Art Talk. And then finally, there's a talk by the Play folks called No One Likes Crashing or Janky Apps, which is true. And that's where they talked about the dashboard and some of the other facilities that they're providing for developers. And that is the talk.
All right. Thank you.
Thanks.